Hello everyone. So today we will see in the overview of how is working the LSM tree architecture. Okay, this is part of the database internal when you are trying to do something like an key-value storage. Okay, and the context that I will talk in this moment because actually I will try to explain how it's working this tree architecture. It's come from the book of the same data intensive application book, the 2026 edition. Well, thank you for watching this video again, and okay, we can started. Okay, maybe we can start with something simple. Okay, and a database only have a two purpose: to get the data and to store the data. Okay, so and the way that is implemented this kind of system is like a black box because you only worry about that which query you have to run to get data and update it. Okay, but actually, if you are a software engineer, it's very important to know how is working the data internals database. Actually, it's not all. No, maybe you don't worry about how is the algorithmic implementation, but you have to know an idea that how is the optimization to get the data or store it. And actually, the problem is that there are multiple approaches that this data internally is implemented in multiple databases. And in this moment, I will only show a single of one, but in the next one, maybe we can do a compare about multiple approaches of this black box. So imagine if you want to create your own database, like a key value storage. So you have to support two methods, write and read. Okay, if you want to write, you have to send the key and the value, and read only you have to send the key to receive the value. Okay, so in this kind of a system, it will be very easy if you only to support the writing side an append log. It's like you have a file on the disk, and in each writing method, you only create a new row, okay, in this file on the disk, and it will be overwritten the key that was stored previously in the file. Okay, imagine that you have in your file, for example, this case, the key one, and the next one is method was generated with a key 2, okay? And then finally, the new one, it will be the overwriting of the old one, the key 1 with the value 2, okay? And if you want to read them, obviously it need to find the latest key of this overwriting system, okay? But the problem is that this kind of system, actually, it will be very fast to append or write something, because when you write something, you don't need to search where is stored, and you need to update it. In this case, always it will be in the append log, right? And if you want to read it, it will be slow, because if you have the bad luck that you have to find the key in the first row of your file disk, actually it will be expensive to search. Okay, so in summary, if you want to improve this kind of system, you can introduce a concept of index. Okay, so index is very simple. It's actually a data structure that you have in a particularly sorted, okay, that it will be easy for you search data in this structure, and finally to get the offset to match with the main file system, the main file that you have the value of the storage. I mean, imagine that you have two structures, okay? The structure or the key value that you already have, and it is in an append log that always is increment the number of rows, because there will be an overwriting, okay? And another data structure that all have in the list of the with some kind of sorter of keys, okay, to find which is the latest offset, right, of the main file system, okay? So actually, the benefit or the advantage to this kind of system is that, okay, we have the problem of the append log that the write is very fast, because it's only an immutable file that you increment the number of the logs, okay? And that read is very slow, because you have to find which is the latest key generated in this file. But if you introduce the data index, the gradient will be slow because actually in each an append log you have to maintain in which offset is generated this latest key, okay? But actually it will improve the read side because if you want to get a key or the value of the key, you have to search in this data index to finally get the offset and directly to get the value of the append log. Okay, but we have to take in mind that the data index not have to be on that disk because actually it will be expensive if you write something in another file. Okay, so for that reason, actually, the index is stored in the memory, and that's called like a hash map index because we have a key and the value that is the offset. Okay, so in this case, actually, we have a super simple example that how is working this hash map index. Okay, we have the RAM storage that we have the hash map. Okay, we have the list of the keys and the offset that you can finally get in the disk append log that you already have. Okay, this hash map index will introduce some problems about this approach. Okay, so it started with if you restart a server, you need to regenerate again the hash map, okay? And it will generate a problem. Actually, you have a huge number of keys. For example, imagine that you have 100,000 of keys or 1 million of keys. Actually, you will need to search or read all the document to finally find the key that you want to get the offset. So there could be improved the way of implementation of hash map, but we can iterate more. Okay, so the next thing that maybe we can evolve is that instead to have an append log and only just a hash map is the concept of stored string table, okay, or also call it like a SSTable, okay. That the concepts meaning that you will have two data structure, okay, to store the key values that you have on your database, okay. Imagine that you have is stable this, but is composed with multiple blocks of files that have a way of a structure like a B-tree order that you have a tree of order, okay, in this case, and you have another data structure that works like a hash index, but with a different way. In this case, it's called like a sparse index. And actually, the way that you is this sparse index is a relation with stable is that, for example, if you want to find an word between handbag and handsome, in this case, you only need to search or see the byte offset to compare the key that you want to find. And finally, seeing the difference of those keys, you can find which block element of a stable is located this key, and you only just need to find with an order in this stable efficiently where is the value that you need to extract, okay, or retrieve. So that's it. And if you want to um, insert more data, there's other approaches, okay, but we can deep more in this moment. So maybe we can see what is a regular flow if you want to implement this kind of system, okay? Again, this concept is come from long storage merge tree workflow, okay? This is a regular flow that you want to implement something like an AQ value system, okay? So starting with a request, okay? If you're trying to write something, start with a request and write, and it will persist in a data structure that is called like a write ahead log. That is only a log on a pen log that you have. It's like a history of all the write requests that you have in your storage. Okay, only it will be safely for you actually if there is a crash recovery or something like restarted the server and you need to recover the data that was stored. Okay, so in this case, the first thing that it will be persist on the disk, and in that part is in the write ahead log. Okay, the next thing that it will be occur is that it will be generating a balanced tree. And that's mean that you need the system, it will internally, it will be generate an order with a tree, right? And it will be stored in the RAM. In this case, Memtable. That it will be stored only the recently change that was generated in this write ahead log. Okay. And finally, when having a time, having a size that was defined, okay, in this system, it will be generating a SSTable that it will be immutable. It's like all the change that come from Memtable, it will be stored in these SSTables because there is not a single file. Actually, there are multiple segments that is sorted with different layers. Actually, it will be stored in the disk. Okay, so if you actually want to get data with this workflow, first it will be pass, it will be a search in on the mem table if there is a recently change that is stored in there, and finally if it is not it is not there, it will be find it in the SS table. That is the flow. Okay, like I said, SS table have multiple segment like to work like in a multiple files. Okay, and there will be a moment that this segment had to be merged because actually it could be the data overwritten. Take in mind that okay, we have an agreed have a log that obviously is in the history of all the change that was generated before, and the SS table actually have an ordered that it will be generated by this write ahead log with multiple overwrited. Okay, but in some moment we need to merge all the segments generated with in a single file. Okay, to increment that to support more segments. Okay, like I said, that stable actually is composed with multiple files or multiple segments with multiple trees sorted. Okay, there will be in a moment asynchronous on the background that need to be merged in everything and will generate in a single file to support more stable in the future. Okay, so the idea basically is to work with the segment and try to merge it in a single segment. Okay, and we have to introduce a concept of tombstone. Okay, so the idea is that, for example, if you already have a key value and there will be a moment that was removed, okay, it's not an hard deletion in this immutable stable. Actually, only we have a tombstone to determine that this key it was removed. Okay, so in that case, at the moment that we are trying to do an merging, we will generate a single file with all the chains, and it will be removed if there is an tombstone. Okay, and that moment, in that moment, it will be deleted in the new segment. And there are compaction strategies to generate this merging. Okay, you can use the size direct compaction. That means that you have multiple SSTables and you need to merge it, and obviously you have to generate a temporal file with all the segments, and it will be remove the duplicated data or the data that was deprecated or obsoleted, right? And finally have a single one that in theory not is the size of this file is not the sum of all the segment because you will remove the obsolete data. Okay, that is called like an size direct compaction. Okay, and another way is when you have the segments like in a layers or labeled compaction. It's like the newest tables. It will be composed like an range of data. It's like okay, first you start with the segment that the range of the keys it will be evolved from the letter A to letter N, okay? And another one it will be M with a letter, I don't know, B, example, okay? So that is composed like an a level, okay? So at the moment that is introduced more data, it will generate more levels, and each level it will have a more number of blocks or segments or range. And the idea is that if you want to search something in some level, you will start with a new one, okay? And if you don't find the value in that level, you have to deep more and deep more, okay? That means that is the compaction of these SSTables, okay? It's not a single SSTable or multiple SSTable that have on the same level. In this case, there are multiple levels that is ordered like the news created and the old created, okay? That is the idea. Okay, the next question actually is how you can find a key in this list of segments with multiple levels and multiple versions, okay? And that's they introduce the concept of Bloom filters, okay? Take in mind that all the segments have a hash keys or hash index, okay? So you only need to use the hash index of this segment to know if actually the key that you want to find is located in the segment. Do not need to read the segment unnecessarily, okay? It's not always secure that the data is there. Actually, there are false positive, but it will be better that compare if you have to read all the files, okay? So in this case, I will introduce the concept, okay? Take in mind that all the segments have a hash function. And in this case, for example, if we have a segment with a hash bit map, okay? Okay, take in mind that the segment, the function of the hash map of this segment, it will be composed with bytes, okay? And actually 2 bytes, okay? But there will be multiple. Okay, the logic about blue filter is that the function to generate a hash on the segment is composed with bitmap. Okay, so in this case, for example, we have a segment have a list of bytes that in this case was generated with this logic. Okay, we have 16 bits here, and we have 2 values here, right? 0 and 1, okay? So if you have a key that you want to find in this segment, you have to you have to reduce the function to generate the hash, okay? And finally, it will introduce this number, right? And you have to match if the value of this index of the bitmap have all them, it will be the number 1. For example, in this case, we have generate this number, okay? And you have to compare, okay, if the index 2 of my bitmap of the segment is 1, okay, in this case is 1, so it's good. And the 9, for example, is 1, okay, it's good. And the 4, okay, we get that is 1 too. So in this case, we have the possibility that is probably present that the value is in this segment. But if we compare it with uh, another key, right, and if there isn't only a single 0 in this bitmap array, you definitely you don't need to read it because it's secure that it's not there. Okay, so that is the logic to not need to read uh, files that you really know that is not there the value that you want to extract. Okay, so that's it. Okay, actually, there are multiple databases, popular databases that use this kind of approach that maybe you can study to learn how you can improve your query performance and stop to assume that y is slowing your query. Okay, so that is that actually Cassandra, RootDB, HBase uses this kind of LSM tree architecture, and maybe the next time that you face this kind of database, you can know how it's working internally, and finally work with the configuration of your databases to improve the performance. So that's all. Thank you for watching this video again, and see you in the next video. Bye bye.